Okay, so in this video, we're going to talk about confidence intervals and then how to run them in SPSS. There was a video prior to this for Mod 1 that you should have watched on the overview of what inferential statistics is to put this all into perspective. So again, from a population, we take a sample. And this is what we study. Now, most of what I'm going to teach is going to use the sample mean just because it tends to be the most understandable. It's also the most used. So there is a population parameter called the sample mean. If we in fact had all the data on a population, or the population mean rather, we would have this actual value, but realistically, we don't ever have actual population data. It's fictional. I mean, the cases when you have a whole population are so small and almost non-existent. But if you actually had all of the data in population and you were to measure every single age or whatever and actually add them all up and divide by the number in the population, you would be able to actually compute a population mean. But realistically, what you do is you take a sample of a couple hundred or something and you calculate X bar, which is the sample mean. Okay. Which is basically what you did a lot of in intro stats. You probably had one professor that had you do one or two of these by hand. It's just an average, really. We don't call them averages because in stats there's three measures in the center and we like to distinguish them. Okay. This is what we call a point estimate. But this in and of itself isn't super duper informative. Let's say I have two data sets, 0, 10, 20, and 9, 10, and 11. In both of these, the sample mean is going to be 10. So the sample mean in and of itself doesn't really tell us all that much about how variable the data are. In the first data set, 0, 10, 20, there's a lot of variability. The second data set, 9, 10, 11, there's not much variability. So the sample mean in and of itself doesn't really give us that information. So what we do is we actually do something called an interval estimate. And we add some information to this. Specifically, what we do is we add and subtract a margin of error. Okay. Which is a value, the margin of error that I'm going to talk more about, it incorporates both the sample size and the variability in the data, and what it will give us is an interval where we have a low end and a high end estimate, and we can look at that interval, and we can get more information about the sample mean in terms of how variable the data underneath the sample mean are. So the interval estimate gets a little into inferential stats, and it tells us it gets fancier and more detailed. It's effectively an expansion of just calculating the sample mean as a point estimate, but we can also give some more detailed information with this margin of error that incorporates the variability in sample size. Okay, so that's what an interval estimate is. Typically, when you're just presenting your data to sort of basics data presentation for the public, you might not give them an interval estimate, but if you're doing something scientific, you then get into not just presenting your sample mean, but also your confidence interval. These specific intervals that we're talking about are called confidence intervals. That's to distinguish them from other types of intervals. We will later in this course see prediction intervals and other types of intervals, but for now, they're basically just expansions of the point estimate to have an interval estimate with a margin of error. Okay. So confidence intervals are interval estimates that expand on point estimates to give a low end, high end value for the range of the point estimate. Okay. And they are computed with a margin of error. Okay. Now, this is in Blumen, and I kind of hate to even bring this issue up because it turns out textbooks, traditional textbooks, which I don't particularly love, tend to sort of distract students and make a much to do about nothing situation. There's an issue when you sample, and this actually goes back to the basics of sampling. I'm trying to learn how to use my eraser, but I don't think there's a lot of hope here. But if we think about this, we have a population and we're sampling, okay? you're getting your sample mean. Well, where does the standard deviation come from? The standard deviation comes from this. So the two parameters we most care about are the mean and the standard deviation. So if you're taking a sample and calculating the sample mean, the standard deviation, as you remember, is calculated based on knowing the mean. So there's no way that we actually know this. So this typically is not known, the population mean. Now you can estimate it with S, but the book talks about the situation where you either know this or don't know this from the population, which is sort of a nonsensical situation. Because if you're taking a sample, by definition, you don't have a population, you don't know the population standard deviation. It turns out textbooks make much to do about nothing because SPSS actually doesn't care one bit about this distinction. But and that's because it limits out. In other words, once you reach a certain sample size, it actually doesn't actually even matter. But Blumen and most undergraduate statistics books make a giant to-do about known versus unknown standard deviation. So the known standard deviation will be the rare case where we actually know the population standard deviation beforehand. That would only occur in some strange situation where there was a previous study that had that information or some case like that in reality. Okay, so there's the known versus the unknown standard deviation. This is reality. For the most part, you don't know the standard deviation. Okay, knowing the population standard deviation is unlikely if we're studying from samples. So what is this? Now, most of our work is going to be based on the normal distribution, which is the black curve in here. This is the normal. These are what we call the t-distribution, or the student's t-distribution. Student's t-distribution is really a modified normal. It's not, I don't want to think of it like, it's a slightly different version of the normal, but it's basically the normal distribution, and it's modified when there's a small sample size, when n is small. Okay. You don't actually have to worry about this running this in SPSS, because SPSS could not care less, because SPSS automatically limits out. There is no selection in SPSS for known versus unknown standard deviation. It doesn't, but in Blumen there is. So in Blumen, you do have different formulas for the confidence interval for mean. Now this right here is the formula, and this is written in terms of the population standard deviation. This is not really known. But the formula is that you have the point estimate plus or minus a margin of error. And the margin of error is this right here, this 1.96 times sigma over the square root of n. So what's in a margin of error is 1.96. What is 1.96? Why, it's the value on the normal distribution, because this is the known population one, and this one uses the normal directly. 95% here. The 1.96, which you should remember from stats 1, is the critical value where the normal distribution would have 95%. So this is your z-scores, and this would be the probability of z being between 1.96. Stats 1 is a prereq for this course, so and that would be 95%, and that's the 95% area of the curve. That's where this value comes from. Then we have the population standard deviation that we don't necessarily know. So you'd have to be given this metric for this calculation to work in this case. And then this is also over the square root of the sample size. Okay. So the sample size affects your margin of error, and it's in the denominator. So the bigger the sample size, the smaller the margin of error. And that's actually important, because the bigger your samples, the more accuracy you can get. Okay. So this is the formula, and this should have been covered in stats 1, so this is kind of sort of review. So this is the formula for the confidence interval for a sample mean when you know the population standard deviation. In the general process, the margin of error is going to be the same components regardless of whether or not you know the population standard deviation. It's just that instead of using this, we're going to use sample values. Okay. Okay. Now, what about the second case when we don't know the standard deviation, which is the usual case? This is the case when, because we're sampling from a population, we don't have the standard deviation because we're estimating it from the sample, which is what we should be doing because that's the whole point. And so we're using this instead. Okay. In this case, the only difference between this and the prior formula is instead of using this value, which comes from the standard normal, we're going to use a value that comes from one of the t distributions. Now, the t distribution is kind of annoying because it's not like the standard normal and has consistent values. The values will actually change. If you look at these little curves, the smallest sample size is the yellow curve, and you look at the values and the density under the curve, you're going to change the value. Like this is the 1.96 for the standard normal. But if you want the same equivalent area for the yellow curve, it's going to be a little bit further out because you can see like the area under the curve situation. So you're going to have like a slightly two-ish bigger value to use instead of this. Is this super duper important? No, because SPSS just incorporates this for you. It is, however, like a textbook theory thing. Okay. So the margin of error will always have this value, which is a critical value from the distribution, the standard deviation either from the sample or hypothetically from the population, and it will be the square root of the sample size, where the sample size, even though it's the square root, it's still in the denominator. Bigger sample size, less error. Okay. Technically, the t-distribution is using your sample size is 30 or smaller. At that point, it doesn't make any mathematical difference which one you're using because the t-distribution and the normal distribution become the same. SPSS just incorporates this directly, and there's no selection feature in SPSS for whether or not you know this population standardization. So just so you know, and it's kind of like, yeah, this is still kind of an issue in the books, but reality is the overall picture is the idea of a confidence interval for mean, add, subtract the margin of error. The calculation details for the margin of error are technically different when you have a smaller sample size and you're using the t distribution, not the normal. But these days, in the old days, it would matter because you're using tables in a book and, you know, the professor's making you do stuff by hand. SPSS just accounts for this automatically. Okay. So this is the modified formula for the t distribution, which really is not substantially different from the other formula if you think about what this is doing. Now, this is written as what's called a compound inequality. I don't particularly love these things with these double inequality symbols. I typically write my intervals as like low end, high end. That's just me. The other way to do that is the plus minus. So this is the x bar minus e, the x bar plus e. Okay. This is the compound inequality like symbol thingies. I don't particularly like these kind of like algebra-esque ways of doing things. This is, so the formula for E changes to T alpha over 2 S square root of n. The parallel here is the 1.96 sigma square root of n. These are really the same formula, except this is the normal value, and then you had to you would get a t value. Now, why is there not a hard-coded value here? Because the t distribution, unlike the normal, will actually change depending on your sample size. So the actual value that marks off 95% is going to be slightly different. And then this formula uses s instead of sigma, and then still over the square root of n. So that's what a margin of error incorporates. It's incorporating the variability, sample size, and a critical value of a probability distribution. But the big picture is that you understand that these interval estimates give us more information about our point estimate by adding and subtracting a margin of error. And they're really easy to do and understand. So this is topic 1. Okay. And I'm going to illustrate these in a minute in SPSS with some actual data. Like, you are not going to ever do any of this by hand in this course. You may have done some by hand in Stats 1, but we are a SPSS technology-driven course, and you should have had a more elementary course that covered this. Okay. There's one other issue, and that's this issue of level of confidence. Now, what a confidence interval means, we use 95% typically as a boundary. A 95% confidence interval means that 19 out of 20 times the true mean, now, you know, because we're taking samples and we're trying to estimate the true population mean, the true population mean will be in there 19 out of 20 or 95% of the time. In other words, there's a 5% error, but oh well, we have to have a little bit of wiggle room here. You can also do these at different levels. I technically don't. Again, this is mainly a textbook thing. I was a professional statistician for years. I have quite more than 100 publications that I was a statistician on. I have never seen 90 or 99% used for confidence intervals. But maybe they are. I don't know. My fields were primarily medicine and some education stuff. Other fields might use these. I don't. And you could also do them at the 90% level, which would adjust it so that 9 out of 10 times the interval contains a true mean. You could also do them at the 99% level, and that would mean that 99 out of 100 times you would get the true mean. So basically for these, you're almost certain to have the true mean. Why not just use these all the time? And the answer is it's not that simple because there's a trade-off of making other errors. And it turns out for most purposes, a 95% interval is the level that is most commonly used and most important. So my level for the most part is the 95%. This is accounted for in the test statistic value, or not the test, the critical value test statistic is actually something different. So that's why this is the 1.96 for the standard normal. If we use 90%, we would have a slightly different value. If we use 99, we'd have whatever the values out here, like 2 point something. So that's where that would be accounted for in the hand formula. And we can do these in SPSS. Realistically, 95% is pretty much always the game level for this. Okay. So now we're going to go into SPSS and actually run some confidence intervals. Okay. Note again that there's no such thing. This is what we would call like a t-test kind of. This is a t-statistic method. This should actually say t-statistic versus the z-statistic. There is no distinction in SPSS as to which is which. Okay. So next I'm going to actually go in SPSS and demonstrate to you how to make a confidence interval. Okay. And there's a data set called eggs that at this point you know how to open. It's this right here. These are, I'm leaving the old videos up, but you don't need those. They're there for reference. But anyways, let's go in SPSS. Now I already have the eggs data open. This is what it looks like. This is data that I collected a couple years ago. It doesn't need to be super current. This is egg prices, which have since quadrupled. And the column color is whether they're brown or white, and then organic, yes or no. And then the price, these are all for a dozen, so it's consistent. And so this is just data on eggs, egg prices. And I'm going to do a confidence interval just for the price overall. I'm not actually going to look at these yet. This is, I made this up to be like, this is my data. I made it up to be like a good teaching example. And so the price column is a continuous variable that we can do a confidence interval on. We could again go under analyze, descriptive stats, descriptive, just to look at our basics, and then hit that, and then to look at our mean and standard deviation. So the mean price is $3.53. The standard deviation is $1.40. They're kind of variable, but not super variable. The min is $1.18. The max is $6.99. There's 40 samples. So that's our basics. But we want a confidence interval. Turns out, to my sort of dismay, SPSS sort of just kept growing, and like it wasn't planned from like top down last year and like super well organized. So you would think that you could do a confidence interval under descriptives or frequencies. You can't. So these two, frequencies, as you know, is kind of my favorite. You can't do it under descriptives. You have to go under explore, which we've talked about. So under explore, you want to select price. And then you only want your statistics in this case. We don't really want to look at plots for confidence intervals unless you do. And then you want to go over to statistics, and then it's actually already clicked off for you to do a confidence interval at the 95%. And then you go ahead and just click continue. And sometimes my SPSS is super duper slow, painfully so. Oh, there we go. Maybe I didn't click it. And then we have our confidence interval. Now this is it right here. So again, we have the mean of $3.53. It is computing for us a 95% confidence interval, $3.07 to $3.98. That is our confidence interval. And so that tells us that 19 out of 20 times, if we took a sample, our true value of the mean for the sample would be in this interval. Now, this is a 95%. We could also run them at different levels. Note it defaults to 95%, which is good. I like that. But we could also run this under Analyze, Descriptive Stats, Explore. That's the only one that will run confidence intervals as far as I know. I got rid of the graphs by hitting display statistics because I don't really want stem and leaf plots and stuff for this. Go to statistics. You can change the level. So I can change it to 90. Okay. So to do the other levels, you want to go under Analyze, Descriptive Stats, Explore, Statistics, and you want to adjust this to, in this case, 90%. Click Continue and OK. And this will give you your 90% interval down here, 3.06 to 3.4. That's interesting. They're slightly different. Anyways, and then I'm looking at these. .07 to 3.98 was the 95. The 90, I got 3.15 to 3.9. And then the 99, let's do that. We go Analyze, Descriptive Stats, Explore, Statistics. You need to change this to 99. Hit Continue and OK. And then down here we got 2.82 to 4.08, and that's correct. And then back in the slides, right here, this is the summary of the different intervals and what they look like. Again, typically you're going to do 95% interval, but it's good to be able to do the 90 and 99. SPSS does not let me run them all simultaneously, which I find a little bit annoying because I'd like to just run them all and have them all on the same display. The 99 means that 99 out of 100 times your true mean is in there, which is incredibly, quote, good on the one hand, but there's other statistical trade-offs with having that level of detail that are not necessarily great. So the 95 turns out to be a balance between making different errors and being a better level to use. So that is how you run, this whole video is on refreshing what a confidence interval is, how they're calculated, what a margin of error is. The issue of known versus unknown standard deviation is automatically accounted for in SPSS, and then how to run and do these in SPSS. Thanks.